Hello, in this video I'm going to talk about the power delivered by a force. We already know that if an object is acted upon by the constant force F, then after the object has moved through a distance of s, the work done by the force on the mass is given by F times s. If we differentiate both sides of the equation, we'll get dw dt is F ds dt. This is because F is a constant force. dw dt is of course the rate of work done, which is of course power. ds dt is of course velocity. So we get this formula: the power delivered by a force is given by F times v. So the power delivered by a constant force is not constant. It actually depends on the speed at which the object is moving. Since we are talking about a constant force here, the acceleration must be constant. This means we can use all the Souvert equations, all the equations of motions, to figure out the relationship between v, s and t. So the vt graph is a straight line graph. The v squared versus t graph is a quadratic graph. The v versus s graph is a square root graph, and the v squared versus s graph is a straight line graph. Since power is F times v and F is a constant, it means if we plot P versus T, it should also be a straight line graph, which means the power delivered by the force increases with time. Or we can think about the kinetic energy of the mass. Since Ke is half mv squared and half m is a constant, that means if we plot Ke versus time, it should also be a quadratic graph. This means the mass should be gaining Ke at an increasing rate. The Ke of course comes from the work done by the force. So Ke increasing at an increasing rate must mean that the power delivered by the force is also increasing with time. If the Vs graph is a square root graph, then the power versus displacement graph is also going to be a square root graph, simply because P is F times V and F is a constant. So both these two graphs are telling us that the power delivered by the force increases as the motion progresses. Just that with respect to time, the power increases in a linear rate, but with respect to displacement, the power increases in a square root manner. Coming to the last graph here, if we think of Ke as half mv squared and half m is a constant, then Ke must increase linearly with displacement. This is actually quite obvious if you remember that the Ke of the mass of course comes from the work done by the force. So K is actually F times S, which means the amount of Ke gain is directly proportional to the displacement. So the Ke should be gaining at a constant rate with respect to displacement. Anyway, so a force can deliver energy to a mass. The amount of energy that's delivered to the mass depends on the distance that the object has moved through. But the rate at which the energy is supplied to the object depends on the speed at which the mass is moving. Alright, that's all. Ta-ta!